Hello, Mr. True again. We're going to now start learning how to describe distributions with numbers as opposed to just describing their shape, center, spread, and outliers with a more visual inspection. But we're going to put some concrete numbers on those, more thoroughly go over the 5-number summary, and especially after this video, how to and what does standard deviation mean, and break it down into very, very small parts. So please, if you would, like a organized set of notes for your class, if you don't already have some, hit pause and copy these. Okay, so Mr. Trueback, we're in the next section of the textbook, and because of how I give my notes, a lot of these vocab words and even some of the formulas and the descriptions you will have seen in a previous video. But to rehash, we're going to describe distributions with numbers, and one vocab word that I have not emphasized very much yet, only I have said it, is this idea of resistant. Now, a resistant measure is a measurement that is not strongly affected by outliers. And my example is here. Very simple examples, 4 numbers, 1, 2, 3, or 1, 2, 2, and 3. If we look at these 4 numbers, we have a mean of 2 and a median of 2. Great. 2 measures of center, they're equal because my distribution is symmetric of my 4 simple numbers. Now, if I bring in the dark, evil outlier of 100, well, now my mean jumps up greatly. When I take these 5 numbers and add them up and have to divide by 5, my mean varies very, very much. It goes from 2 to 21. That's a huge difference. The reason why is because when you calculate mean, you have to use all of the data points. Well, when you add in that 100, it gets thrown into the calculation. Whereas the median still stays a value of 2. Now, to be resistant, the mean is not resistant. It changed greatly due to the outlier. The median, now is a resistant measure, and it doesn't have to stay the same. The definition of resistant, it is not strongly affected by outliers. Now, in intro to statistics, we actually have just a very small number of measurements that are resistant. We have median, we have the IQR that is calculated through the median process, so the IQR is resistant. And if you want to say the mode is resistant as well, you can, though that's not something we normally worry too much about. But really there's only 2 measurements, if you want to include mode, 3 measurements in statistics that are resistant. Median, the IQR, which uses the median in its calculation, and maybe if you want to consider mode. Everything else in the book, all the other formulas you're going to learn this year, are going to be not resistant, are going to be heavily influenced and affected by outliers. So, the mean. The mean, again, closest to the tail of a skew distribution. Here is the formula for calculating mean. You got this really scary looking Greek symbol in it of summation symbol, and don't fret, you've learned and have known how to find mean for years now, and you know to find mean, you just add all your numbers and divide by how many you have. That's what this formula says. Add all your individual with the x sub I, add all your individual x's, and then when you're done, multiply that by 1 over n or divide by how many numbers you have. So statistics formulas are a lot scarier than they really are. That Greek summation symbol just means add over and over and over again, which is why we love graphing calculators and computers now to help us with our statistics. We just learn the concepts and learn how to analyze and let the computers do the grunt work. X bar is the sample of a mean, or the mean of a sample, and mu is the mean of a population. This will always be given to us, never calculated by us in intro to statistics. The measure of center for bell curves. If you have a bell curve distribution, a unimodal symmetric distribution, you want to use the mean. That's the best measure of center for a symmetric distribution. Means are not resistant. I seem to have somebody at the door, so I'll be right back. Okay, so here it came for a textbook. And we're back. So the mean, closest to the tail if you have a skew distribution, the formula, measure of center, the best choice if you have a bell curve, and again, it is not resistant. Median and IQ are the only resistant measures that we have, and if you want to throw in mode, that is fine. Okay, median, measure of center we've talked about already quite a bit. used for non-normal data. It is the middle number or the average of the two middle numbers. And the median is resistant, like I just said twice now, which is why it's the best measure of center if you have non-normal data. Let's key on this idea of the median as the middle number or the middle two numbers. We've had some problems in the textbook about if you have a group of people, let's say 10 people, and their average income is $40,000. Well, if I tell you out of those 10 people the average income is $40,000, I can just take $40,000, multiply it by 10, and say, okay, everyone makes $400,000. I can do that because when I say the average is $40,000, I've added all 10 of those numbers up and divided by 10. The middle number, or the median value, only is calculated using the middle number or the middle two numbers. So, if I tell you that 10 people have a median of $40,000 of income, how much do the 10 people make in total? I don't know. I only used one or two numbers to calculate the median. I don't know how small the other numbers are, the other, what, 4 or 5 numbers? And I don't know how large the other 4 or 5 values are. I say 4 or 5 because you can vary a little bit how you find median and what you do from there. So you need to realize how the difference in the calculations of mean and medians and how they can affect some of your questions from the textbook. Again, it's resistant. Quartiles, I gave an example of that on a previous video. If you want to find quartiles, you take low to high, find the median. Take the first half of your numbers, find the median, that's Q1. Take the second half of your numbers, find the median, that's Q3. Again, if you want an example of that, look at the previous video. All right, so going over to some more summaries. We've got the 5-number summary, which I have just maybe mentioned in passing. I kind of forgot what I've said by now. And range and percentile. Some of these values have again already mentioned, and we're moving into a graph called a box plot in a minute. So here's some other concepts in section 1-2 of my textbook. You'll also maybe have seen these in other videos because I repeat myself a lot in the beginning of the year, can't give notes when no one knows a clue about what you're talking about. 5-number summary, that's min, Q1 median, Q3, and max. The graphical display of a 5-number summary is a box plot. The left whisker is the min. Where the box starts is the Q1 value, median, Q3, and max. We're going to break that apart again here more in a minute. Trying to make sure I don't run over time. Your range, again, I've said that a number of times. That's the max minus the min value. The range is one singular value. So if your low is 20, your high is 100. Your range is 80. Don't say it ranges between 20 and 100. I used to do that and got corrected eventually after a few years of teaching. A little bit late, but anyway. Percentiles. You know, if you take the SATs and you score in the 95th percentile, then you scored better than 95% of all your fellow students. Graphical display, we just covered that, was an ogive graph, or a relative cumulative frequency distribution. So make sure you go look those up. Let's talk a bit about box plots. They are our graphical display of a 5-number summary. They display it, okay, great, and once more time, your 5-number summary is what we use to describe the shape of non-normal data. It's not written up here because I haven't talked about standard deviation a lot, but if it is a bell curve, a symmetric unimodal distribution, your best description for shape is not the 5-number summary, but mean and standard deviation. We'll talk about that later again. Box plots can show skewness, but not gaps. So let me explain what I'm talking about there. Here we go. So here is a box and whisker plot. Okay, we talked about left skewed and how if it was left skewed, the data would just sort of taper off to the left and become more spread out. Does this box plot look left skewed? The answer is no, because these 3 quarters are all very evenly spaced with just one long whisker. That is probably due to an outlier. To show skewness, it would need to, and it won't be perfect, we always deal with real life data, so this will vary, but you're looking for your segments to kind of increase in width as you go either to the left or the opposite would be right skewed. This would be more like a left skew distribution with a tight upper 25%. As I work my way down towards the minimum, my gaps get farther and farther apart. This is skewness. One thing I did not write up here, though, is one of the very best uses of box plots. They're not to analyze the shape of the data. That's what we have histograms for. No. If you go into your calculator, you can put data in 1, 2, or 3 lists, and you can display up to 3 of those box plots at once. You'll also see examples in your textbook where there's multiple box plots together, maybe up to 4 or 5 of them. You want to use these box plots for comparing multiple distributions. You put those on the same x scale, usually x, sometimes your book will put them vertically, and when they're side by side, then you can talk about any comparisons or contrasts you see between these. With these being the medians, maybe the data values that these two box plots now represent that I made up, that I don't have any numbers, but the median values are the same, but this grouping of data have a much smaller range or a much smaller spread. Or later when we're talking about standard deviation, a much smaller standard deviation. All this box plot shows that the data is more spread out. This might actually have more numbers here than up in this graph, because we can't see how much data is displayed, just how far it's spread out. This min is smaller than this min, the max is greater than this max value, and the medians are about the same. Remember, if you are describing distributions of shape, center, spread, and outliers, I'm just doing a quick overview. Well, I just repeated here what this says, and I think I'm running off the screen. Let me see if I have any time left. Yes, I do. All right, so one last concept before we call this video a wrap is modified box plots. Now, we are going to have a video, actually we've already done a video of how to find histograms and box plots with our graphing calculators. So we definitely want to make sure we know how to do that. But I haven't introduced it on an official set of notes yet. So modified box plot, those are awesome because they take care of the IQR test for us, which means that they'll show us the outliers with individual points on the side. And I just talked about how to find the IQR, how to do that IQR test. It's the IQR range, which is Q3 minus Q1 times 1.5. You add that number to Q3, you subtract the number from Q1, and you get this boundary, this imaginary boundary that you don't want your data to fall outside of. Well, your calculator will do that for you. And when you see this box and whisker plot, or box plot, your whiskers will start and end at the first or last piece of data that actually passes the IQR test. So if the lower bound is maybe 40, but the first piece of data that's greater than that lower bound is 50, that whisker is going to be at 50, not at the 40, not at that imaginary lower bound we've set up by doing the IQR test. You definitely want to choose these out of the calculator because why not get more information out of a graph automatically if you can. Well, we're going to erase all this, start talking about standard deviation in a second, and talk about all the properties of standard deviation, which is the most important measure of spread we're going to talk about this year in Intro to Statistics. Bam!